Hello, crazy kids. I'm going to go over some nuclear chemistry with you so that you feel better about researching your project. The first thing I want to hit is just some of the pictures that you see on here. To the left, you'll see a picture of an atomic power plant or a nuclear power plant. What you'll see there, it looks like two capsules of some sort. And those capsules are actually containment buildings. And the nuclear reactors are within those containment buildings. Now, in the United States, there are structural requirements for a containment building to be around the nuclear, where the nuclear reactor occurs or where it takes place. And so, in Chernobyl in Russia, they did not have those requirements. So that's one of the reasons why Chernobyl was so terrible, was because the radiation was instantly out into the atmosphere. Now, those containment buildings, they can't hold everything, but if there were to be a nuclear meltdown, those containment buildings can keep a lot of the radiation contained. What you'll see in the top picture there, you'll see a woman who's getting some radioactive xenon. And what happens there is that radioactive xenon or other radioactive materials can be pushed through someone's body to show and to find maybe infection sites or tumors, or can show the blood flow through the body. So it's kind of like it works with different equipment, medical equipment, and it shows and lights up areas of difficulty or weakness in your body. To the right there, you're going to see a smoke alarm, and smoke detectors contain americium, and americium is a americium 241 in particular is radioactive. And if you ever read about it's called The Radioactive Boy Scout, and his name was Hahn. His last name was Hahn. But what he did was he was trying to build his own nuclear reactor, and so he needed radioactive materials. So he would often go to hotels and steal the americium from the smoke alarms. So you should look up that story. I think his name was David Hahn. It's a pretty crazy story. And there toward the bottom are strawberries, and they're treated, it says, by irradiation. Basically, that's like an ultraviolet kind of light source going on there. And that's the last source that it's exposed to before, you might find it in your grocery store or something like that. Because a lot of times that basically kills bacteria or pathogens, making, your food safer to eat. Now, obviously, if you eat organic or anything like that, it's not going to be exposed to that. So, Marie Curie, you definitely need to know her name with radioactivity. Marie Curie was the one who actually discovered radioactivity, and she discovered that actually sometimes elements that were either heavy or unstable would actually disintegrate into smaller pieces on their own. So when it says spontaneous disintegration, it doesn't necessarily, radioactivity doesn't mean that you need something to start the reaction. Sometimes, if you want to start the reaction, like when you guys are looking at the atomic bomb, we wanted to start the reaction of uranium. Then you can shoot a neutron at it, and that's kind of like a catalyst of the reaction. But typically, things just, disintegrate on their own. It's just spontaneous and just starts to disintegrate. Some things have a super long half-life, like bismuth has a half-life of 6 billion years approximately. So bismuth hasn't even been through a half-life yet. Whereas the element tennessine, which is atomic number 117, tennessine has a half-life of about 3 seconds. So really, there's not much use for tennessine right now. And that element, by the way, was discovered in the Oak Ridge Laboratories near Knoxville. So a big thing here is I want you to understand the differences between nuclear reactions and chemical reactions. And chemical reactions actually involve the electrons, where nuclear reactions, they involve the nucleus, obviously by the term nuclear. But the nucleus actually opens up, and that's where the energy comes from. That's the crazy part, because that energy that's holding the nucleus together is called binding energy, and that's a huge amount of energy. Well, nuclear reactions cause that energy to be released And that's why nuclear reactions create so much more energy than chemical reactions, because chemical reactions are just electrons either sharing or giving or taking, and they're forming bonds. Where nuclear reactions, there's actually a huge amount of energy being produced from the nucleus. Now, this is something you may or may not be familiar with, but good old Einstein's equation E equals mc squared. I'm not going to teach you so much about this because I truly don't know so much about this. However, this is the crazy part, is usually everything on this planet is either mass or energy. Well, everything can be described as either mass or energy. In this case, typically mass, when mass is converted, the law of conservation of mass, basically it's converted to mass, and you don't lose or gain any mass. When energy, law of conservation of energy, energy is neither created nor restored. It just changes, where it's at. Here it's like we're pushing mass into energy, and this is very weird. And where that mass comes from, that mass is coming from the nucleus of the atom. And typically, if you look and you have a different mass for an atom because of an isotope, that's where the mass is going to come from. And it's just a little bit of mass, but that little bit of mass can create a whole lot of energy, especially since we multiply it by the speed of light, because that little bit of mass is increasing in velocity, which increases in energy as well. Now, there's three types of radiation: alpha, beta, and gamma. And we're going to take a look at these three types and just see how each of them move. I'm not so concerned right now about like what they look like if they were in a nuclear equation, but I want to see how they move. And that comes from the penetrating ability. Now, an alpha particle can be stopped simply by paper. It can be stopped by your clothing, by your skin. Where beta, instead, it's going to need something a little more, and it could need about a half a centimeter of lead, or it could also, our school's building, the walls, multiple layers could stop, or it could help stop a little bit more beta. Gamma is going to go straight through something until it hits something that's 10 centimeters of lead. Now think of it, 10 centimeters is about 4 inches. So think about, that's why you're being exposed to a certain amount of energy when you get an x-ray. So even if you get, if you go to the dentist and you get x-rays on your jaw, they put that kind of like cape on the front of you, and that's a leaded cape because your body, they just don't want your body exposed to unnecessary radiation. Your body is going to be exposed to radiation every day to a teeny tiny amount. However, x-rays and stuff like that, of course, it depends on how many you have in your lifetime, but we want to try to prevent exposing you as much as possible, and also to protect the person, the radiologist, giving the x-ray. This is what I want you to think about with the chocolate chip cookie dilemma. So pretend you have a chocolate chip cookie in your pocket, and let's think about which cookie we'd want to eat. A cookie that is bombarded with alpha particles, beta particles, or gamma rays. Okay. So right off the bat, you're probably thinking, oh my Lord, a cookie bombarded with gamma rays? No way. That would be terrible, terrible, because gamma is by far the worst kind of radiation. And you are right that gamma is by far the worst kind of radiation, but that is not the worst cookie to eat. So if you had a cookie in your pocket, you're going to have, if alpha particles are shot at you, your clothing is going to stop the alpha particles, or if you put your hand in your pocket, it would stop the alpha particles. So we're not going to be too concerned about alpha particles. Beta particles, however, if beta particles are shot at you, multiple layers can stop those beta particles. So maybe put your hand in front of your pocket and then your clothing, and then it gets into the cookie, and then it's probably absorbed by the cookie in some amounts, because all those beta particles are not going to make it through the cookie. Now, if you were bombarded with gamma rays, those gamma rays are going to go straight through that cookie, straight through your body, no problem. Those gamma rays, though, when it goes through your body and your body's living, those gamma rays are going to they could damage the living cells. However, those gamma rays, if they go through something non-living like cookies, okay, but those gamma rays went straight through it. So actually, the worst cookie to eat would be one that's actually affected by beta rays or by beta particles. And because those beta particles are going to be the ones that are actually absorbed by the cookie, and by you eating that cookie, you're going to obtain more radiation into your body. So these are just some things I want you to think about that will help you in your research and your understanding of nuclear chemistry. All right, take care, you guys.